You have any class after 10 o'clock? If you have any class after 10 o'clock, then I don't know how much time I can give this topic. So as we were discussing the decision boundary, so in the last class we have seen that to classify data point or a set of points and put a label to those data points, we can use the hypothesis representation in logistic regression. Okay, so we can classify the data points or classify the objects in the way a regression model predict a value. That means after predicting the value, we can make it infer uh, to uh, give a class level, and according to the class level we can have a decision that the points or a set of or single point or a set of points may have some class level. Okay, and according to that we can have a plot in the decision boundary. Okay, so according to that we can define a decision boundary, and on one side of the decision boundary we can have positive or negative data points, and on the other side we can have the positive or negative data points according to the decision boundary that we can define. Okay, now what we saw in the last class that in a hypothesis representation, h theta of x, this theta t represent the model parameters and x represent the data points. Okay, and in the logistic regression, what we have seen that g of z equals to 1 upon 1 plus e to the power minus z. Okay, now in place of z, so in this case h theta x equals to g of z. So if we replace z with theta t x, then we can have 1 upon 1 plus e to the power theta t x. Okay, and this will give us this S-shaped curve. So this S-shaped curve means if this is 1, this is 1, then this point is 0.5. So we can have this S-shaped curve which will approach to 1 when z is found to be greater than 0. Okay, and when z is found to be less than 0, then this curve will approach to 0. Okay, so this is basically the asymptotic to 1 when z, this is asymptotic to 1 when z found to be greater than equals to 0. Okay, and it is found to be asymptotic to 0 when z is found to be less than 0. Okay, that means this is the so this is the z for positive values, and this is the z for negative values. Negative means less than 0. Okay, so and what are the other criteria that we have established during defining a hypothesis representation? So in the hypothesis representation, so h theta x would be found to be greater than equals to 0.5 when theta t x is found to be greater than equals to 0. Okay, and this will infer the y to be the positive class or y to be 1. Okay, and h theta x, when h theta x is found to be less than, so this will be found to be less than 0.5 when theta t x is found to be 0. That means this part, okay. And the right of this part is found to be positive for z values, and left of this part is found to be negative for z values, okay. And when theta t x is found to be 0, then we can say that s theta x less than found to be 0.5, okay. And this will infer to have the class level y equals to 0, okay. Now let us consider, we are trying to we are trying to find, or we are trying to estimate the class levels of some data points, okay. These are the data points which are been plotted in xy coordinate. So I don't know what are the class level of these data points. Now we have to estimate the class levels on the use of decision boundary. That means before we estimate the class levels of these data points which are being plotted in the xy coordinate, so we will use the decision boundary, and with that decision boundary we can infer that some points in this data point, in the set of these data points, will belong to the positive class y equals to 1, and rest of the data points will belong to the negative class y equals to 0, okay. So now we have to define the decision boundary, and now in the hypothesis representation what we have seen that in theta t x, theta t is the model parameters, x is the data points, okay. So we can have this representation like theta 0 plus theta 1 x1 plus theta 2 x2 plus theta 3 x3 and so on, okay. Now we don't know what are the values of theta 0 to theta n, but only we have been provided with this data point. That means we know what are the values of these data points, but we don't know about the parameters, okay, model parameters. So we have to estimate the model parameters in this hypothesis representation. Then we will put these values in this representation and try to figure out whether theta t x is found to be greater than equals to 0, or it is found to be greater than equals to less than equals to 0, less than 0, okay. So when this x is found to be greater than equals to 0, then the predicted value will be found to be greater than equals to 0.5, and in that case we will infer the class level is found to be y equals to 1. Otherwise, when theta t x is found to be less than 0, then we can have the predicted value to be less than 0.5, and in that case we will say that the class level is found to be y equals to 0. So these are the data points which are being plotted in this xy plane, okay. So so this is theta tx, or we can have this is z, okay, and this is h theta x, or we can say this is g of z, okay. This is 0, and if you divide if we divide this domain, then we will see that this is 1 2 3 1 2 3. Okay, now to separate some of the data points or subset of data points from another subset of data points. Okay, now in this classification problem, we have to define the decision boundary. Now what we have seen, theta t x equals to theta 0 plus theta 1 x1 plus theta 2 x2. Okay, so here we have two data points and we have to estimate three model parameters, theta 1, theta 0, theta 1 and theta 2. Now let us consider theta 0 is -6, theta 1. So initially we can assume that these are the model parameters value, and we will fit this model parameters value in this hypothesis representation, and we will try to define a decision boundary. Okay, so initially these model parameters will not be known. Okay, we have to estimate these model parameters, but for sake of discussion, initially we can have initially we can assume these values for the model parameters. Okay, and we will try to fit this data, or we will try to fit this model parameters value in this hypothesis representation. So we can have 6 minus 6 plus 2 into x1 plus 2 into x2. Okay, so what is this? This is theta tx, and what we have to see that whether theta tx is found to be greater than equals to 0.5 or greater than equals to 0 or not, or theta tx is found to be less than 0 or not. Okay, so we have to check both these condition, and accordingly we will infer to put a class level the data points. Okay, so we can write -6 plus 2 x1 plus 2 x2 greater than equals to 0. Okay, now if I take the two common from x1 and x2, then we can write 2 into x1 plus x2, and we take -6 on the right hand side. Okay, then x1 x2 will be found to be greater than equals to 3. So what this So if we try to interpret this, interpret this representation, final representation, x1 plus x2 greater than equals to 3, then we can have two different equations. One is x1 plus x2 or equals to 3, or x1 plus x2 greater than 3. That means the decision boundary that we are looking for would be x1 plus x2 equals to 3. That means at this point we can have this decision boundary. Okay, so decision boundary, we can have a decision boundary over here. Okay, that means x1 x1 plus x2, when the x1 plus x2 is found to be greater than 3, then those points which lie on the lie in this region. Okay, or those points which fall in this region will have the class level 1. Okay, and those points which fall in this region of the decision boundary will have class level 0. That means we can have these points above this decision boundary. Okay, and these points are found below this decision boundary. So therefore, and this is your x1 plus x2 equals to 3. So this decision boundary will have x1 plus x2 equals to 3. So decision boundary is x1 plus x2 equals to 3, and these points will have x1 plus x2 greater than 3. That means whenever we will see that x1 and x1 plus x2 found to be greater than 3, then these points will have the class level 1, and for this data points x1 plus x2 less than 3. Okay, and we will put the class levels to these data points y equals to 0. Okay, now let us consider another hypothesis representation where the model parameters are found to be theta 0 plus theta 1 x1 theta 2 x2. Okay, then we can have theta 2 x3 square theta 3 x4 or x1 square. We can have x1 square x2 square. Okay, so this is the hypothesis representation. Okay, now from this hypothesis representation we need to predict the decision boundary, and according to the decision boundary we will classify the data points either into positive class or into negative class. Okay, so initially we can assume that theta 1 is -1. Okay, theta 0 theta 1 is 0, so therefore this becomes 0. Theta 1 x1, theta 2 0, so this becomes 0. Okay, and here x1, if we say x1 is 1, x2 is 1, if we consider the values of x1 and x2 1, then for this term we can have theta 3, no, okay, so x1 square plus theta 4 x2 square. Okay, so initially we are just we just assume the model parameters values from theta 0 to theta 4. Okay, and we have to predict the decision boundary from this hypothesis representation. So theta tx now becomes -1 plus theta 3 x1 square plus theta 4 x2 square. Okay, so initially we can assume that this theta tx is found to be greater than equals to 0. So now we can have here theta okay, theta 3 and theta 2. Let us consider the model parameters values for theta 3 and theta 4 is 1. So we can write x1 square plus x2 square greater than equals to 0. Okay, so here we are considering the value of theta 3 is 1, theta 4 is 1. Okay, so therefore we can write x1 square plus x2 square. We will see in the next class how we can estimate the model parameters using gradient descent, but before that we try to assume this model parameters value and see the effect by changing this model parameters value in defining the decision boundary. Okay, so previously we saw that when we assume the decision parameters value in this way, okay, manually if we decide the model parameters value and put and fit these values in the hypothesis representation, then we can have a decision boundary like this. Okay, and this decision boundary will separate is used to separate the data points, one set of data points from another set of data points. Or for a single data point, we can also predict the class levels. If we put these data points in the data set and try to estimate the class level of that newly added data point, then we will use this hypothesis representation. And before we define the decision boundary or change the existing decision boundary for the newly added data point, so we have to estimate the parameters. Okay, and according to the model parameters, the decision boundary will change. That means if there is an existing decision boundary which has been defined for the available data set. Now when a new data point is added to the data set, then for that data point we have to again estimate the model parameters. Okay, that means for the new data point, model parameters may be changed. And when the model parameters will be changed, so accordingly the decision boundary, the shape of the decision boundary, orientation of the decision boundary will be changed. Okay, and initially when some points were when there will be a few points which were assigned the class level 1. Now when after adding the new data points, they will be they might be level as 0. Okay, they might be level as y equals to 0. That means initially they were found as class level 1. After changing or after adding a new data point, the decision boundary, the orientation of the decision boundary, shape of the decision boundary may be changed, and accordingly some data points which were labeled as 1, now they may be labeled as y equals to 0. Okay, so there will be some change in the class level of some data points. So after having this representation for the given hypothesis, theta tx equals to theta 0 plus theta 1 x1 plus theta 2 x2 plus theta 3 x1 square plus theta 4 x2 square. So now we can say that x1 square plus x2 square equals to 1. Okay, and x1 square plus x2 square greater than 1. Oh, so greater than 1. Okay, so that means we can say that the equation of the decision boundary will be x1 square plus x2 square equals to 1. So that will give us a circle. This is the equation of the circle. Okay, and outside of the circle can be represented by, that means the points which will fall outside of the circle will have the equation x1 square plus x2 square greater than 1. Okay, so this representation will represent, or this representation will infer the points fall uh, which fall outside the circle will have the positive class. That is, we can say that y equals to 1, or we can label those data points y equals to 1, and those points which fall or which lie inside the circle will have the class level y equals to 0. Okay, so from this decision boundary we can infer this decision about the class level of the data point. So how this representation will be look like? So if we take a visualization of this decision boundary, then we can have this type of. So if we consider this is 0, this is 1. Okay, that means some data points will lie inside the circle, and for these data points we can write x1 square plus x2 square less than 0, less than 1. Okay, less than 1. Okay, and there will be few data points which will be found outside the circle. Okay, and the data points which will be found outside the circle, so they will have the class level y equals to 1. Okay, for those data points we can write x1 square plus x2 square greater than 1. and this equation of this circle would be x1 square plus x2 square equals to 1. Okay, so this is our decision boundary. X1 square plus x2 square equals to 1. This is our decision boundary, and the points which will be found outside the circle will have x1 square plus x2 square greater than 1. Okay, so what we can infer from this representation? We can infer from this representation that the points which will be found outside the circle, we have the class level y equals to 1 or positive class, and the points which are found inside the circle will have the class level y equals to 0 or negative class, we can say. Okay, so now the big questions here is how to estimate these model parameters. Okay, how to estimate the model parameters value, so that we can when we can estimate an appropriate set of model parameters. uh, when we put this estimated model parameters, or when we fit these model parameters in the hypothesis representation, then we can get the error function, so which will be found in the optimal form. Optimal form means where the error is found to be minimum. Okay, so to define the optimal representation of this hypothesis equation, we can estimate the model parameters. Okay, using gradient descent or some other way. We can there are a number of optimization algorithms. So with the help of those optimization algorithm, we can estimate the model parameters value, and when we fit this model parameters value in the hypothesis representation, then we can have the optimal representation of the error function. Okay, now we will be talking about the cost or penalty of the logistic regression. Okay, now in case of linear regression, what we have seen? We have seen that y equals to mx plus c. Okay, y equals to mx plus c, and this y, and when we predict when we predict a when you predict a new dependent variable, so we can have this representation. So in place of y, we can write s theta x. Okay, and for this representation, we can define a error function j theta equals to 1 by n summation over half of yi minus h theta x I square. Okay, so I equals to 1 to n. So n is the total number of, so here n is the total number of data points. Okay, and we are here we are taking this sum is calculated over half of yi minus h theta xi square. Okay, so this part refers the MSE, that is called minimum squared error. Okay, we can have other representation, root mean square, RMSE. So the initial representation for this root mean square error, root mean square error or mean square error is least square error function. Okay, or when we have talked about the least square regression model, so we have found, so this type of representation which is defined for the error function or penalty. Okay, now let us consider we are rewriting this error function as cost of yi comma h theta xi equals to half of yi and h theta xi. Okay, now if we generalize this form, therefore we can write half of y minus, so actual value minus predicted value, and we take the square of this deviation or of these residuals. Okay, so y minus h theta x, or we can y minus h theta x, so this will give us the residuals or the deviations for which we are taking the deviation square of this deviation, and this half is added because we are interested to have the minimum square error. Okay, minimum square error, so that is why this half is added. We so this is not required, sometimes this is not required when we are interested only about the residuals of all the points. Then in that case we will multiply the total number of total number of count of the data points with the sum of square of residuals. Okay, now if we try to fit the equation g of z equals to 1 upon 1 plus e to the power minus z, so in place of z we can write theta tx. Okay, now we try to find the error curve or penalty curve. So what this penalty curve will look like, so this will be look like, so penalty curve will have the form like this. Okay, so this is nothing but the z theta. So basically what happens when we have an objective function like g. Okay, and we have to estimate, we have to minimize this objective function such a way so that we can get the error minimized. Okay, that means that if we minimize this error function, then we can have an optimal penalty, and for this we need to we need to estimate the model parameters such a way that when we fit these model parameters in the hypothesis representation, and then we can get the optimal representation. But here you can observe that the logistic regression, the equation of the logistic regression give us the nonlinear, so non-linearity. So in case of linear regression, what we have seen that there is a linear relationship between the data points, but here when we see, when you introduce this nonlinearity in this error function or penalty function, then we can obtain this type of error curve. Okay, or penalty curve. So in this error curve or penalty curve, we can see that here we have uh, here we have a number of local minima. Okay, but from this set of local minima or number of local minima, we cannot estimate what would be the optimal one. Okay, so this gives the impression of non-convex function, non-convex function. Okay, so in the non-convex function we can have lots of local minima, but among those local minima, so it will be difficult to find what would be the optimal local minima or the global local minima, so which will give us the minimized error. Okay, or minimized penalty. So when we fit this logistic regression representation, or when we fit this value in this error function y equals to cost of y comma h theta x equals to half of y minus h theta x square. So we will see this type of non-convex curve is determined, non-convex curve, and in this non-convex curve, so it is very difficult to find the global minima from this uh, from this uh, from this set of uh, local minima. So so it would be difficult to find the optimal representation for this cost function. Okay, so in other way we can say that it is very difficult to estimate the model parameters from this non-convex representation. So when we put this when we put the value of this h theta x in this cost function, so we can obtain this kind of non-convex representation, and from this non-convex representation, so it is difficult to find the global optima, and that will optimize our cost function. Okay. Now, what would be the alternative solution for this, or how to get rid of these local minimas from non-convex representation? So, if we think about the convex representation, in the convex representation, what we can see that if we start from a random points, okay, if we start from a random one, that means if we consider the linear regression equation y equals to mx plus c, and initially we can consider c equals to 0. Okay, then gradually we will increase the value of c. Okay, and then we will see what would be the change, is found in the error function. So for this linear regression, we can define an error function, and in that error function we will initially put c equals to 0, or the intercept value is defined to be 0. Then gradually we will increase the intercept value, and we will see how the gradient is changing. Okay, if gradient is changing such a way that we can have only one optimal point, so that becomes the global optima. Okay, so without having the local minima, we can reach to the global minima by taking a small step. Okay, so we can start from c equals to 0. So in this case, if we start from here, then we can have this convex representation of the error function like this. Okay, so if we take a small step like this, okay, so in this direction, if we take the small step, then what happens? So here we could have the slope of gradient is found to be 0. That means the slope of gradient at this point, the slope of gradient, what we call slope of curve, we can say slope of curve or gradient is found to be 0. That means this is the flat region. Okay, so in the flat region, its gradient will be found to be 0, or slope of curve is found to be 0. So this slope at this point will be referred as global minima. Global minima. So basically, when there will be an objective function, and we will try to optimize that objective function in terms of model parameters. Okay, that means we will estimate the model parameters in such a way that we will find this global minima by taking small steps in the direction along which we will find no local minima. Okay, so that means the local minima will not be, but in this way we can have this convex representation, and in the convex representation there will be only global minima, so which will give us the optimal penalty or optimal cost. Okay, so if we put this gradient value, so we can start from c equals to 0, then we will put c equals to 0 0.1, 0 0.2, 0 0.3. In this way, if we gradually increase the value of intercept in the linear regression, then we can have this type of convex curve, okay, or convex function. Okay, so this convex function will give us the global minima or optimal representation of the regression function. So this optimal representation or this convex curve will be obtained for the error function j theta, or if we try to represent is another way by rearranging this equation of penalty function, then we can have this cost of y comma h theta x. Okay, and we will fit the model parameter, we will fit the model parameters value by changing the intercept or some other parameters which will be defined for that particular hypothesis representation. Okay, so in this way we can achieve this convex representation, and this is nothing but so we can obtain this convex representation using gradient descent. Okay, so in the next class we will be talking about the gradient descent and other uh, other optimization algorithm. Okay, and we will see how we can optimize an objective function as the cost function, and then we will obtain this global minima or optimal value of the error or penalty. Okay, so initially what we do, we define the decision. First we define the hypothesis representation, then we define the decision boundary. Okay, and from that decision boundary, so we will have some initial assumption of the model parameters. Then we will find we will find the gradient value, okay, in the direction to which we will obtain the global minima. Okay, or perfect convex representation. So when we obtain this convex representation, then we can have the error to be minimum. Okay, or error is found to be minimum. So we will see in the next class how we can estimate the model parameters with gradient descent and other optimization algorithm, and we will try to estimate the model parameters, and we will fit these model parameters to find the minimum error. Okay, that's all for today. If you have any questions, you can ask me.